All right, now we're going to take a look at the plate tectonics phenomena associated with the movement of these tectonic plates. 4 questions I want you to keep in mind as we go through this discussion. Number 1, why are earthquakes concentrated in zones? Number 2, why are there zones of only shallow earthquakes? In other words, they do not go deep into the Earth's mantle. Why are there zones of shallow to deep earthquakes? In other words, why do we have zones where you have shallow earthquakes near the surface, medium, and then deep earthquakes far underground, up to 500 kilometers underground? And why are volcanoes located near medium and deep earthquakes? Quick review of what you've talked about as far as the composition and structure of the Earth, because this will be important for the movement of tectonic plates. The fact that the crust of the Earth is incredibly thin. It ranges from about 5 to 60 kilometers thick. Overall, the thickness of the Earth, the radius, is 6,400 kilometers. The crust is an incredibly thin structure on the Earth's surface. It's so thin, in fact, you can envision if you cut an apple in half, the skin on the apple would represent the thickness of the crust on the Earth. Now, the other key point to remember from previous discussions is that this mantle behaves like silly putty. It flows like a liquid, but it also behaves like a solid. This allows this crust to slowly move over its surface, much like with silly putty. It'll flow if you stretch it or just hold it, but if you pull it quickly, it snaps as if it were a solid. Divergent boundaries go all the way back to when we talked about Pangea and Wegener's early evidence. A divergent boundary is where 2 plates move away from each other. Early evidence Wegener had for this was his breakup of Pangea. He had the idea of matching coastlines, fossils matched, bedrock matched, and lastly, glacial striations matched. All of this evidence led Wegener to believe that the continents were once connected as a supercontinent known as Pangea, and since that point, they have moved away from each other or diverged. A more recent discovery is this idea of paleomagnetism, and this is that study of ancient reversals in Earth's magnetic field. There's a previous video on this one that I strongly recommend you watch that explains this idea of paleomagnetism and its conjunction with divergent boundaries. The idea that the patterns on both sides of this divergent boundary, the magnetic patterns, match. This was quantitative evidence that we have these divergent boundaries. Quantitative because it's igneous rock, we can get radioactive dates for, so we can actually age the different sections of this strata. Properties of these divergent boundaries include a couple of key features. Number 1, you're going to have what are called hydrothermal vents. What happens here is water seeps into these fissures here, gets superheated, and comes back up to the surface, creating these high temperature vents. There's an abundance of sea life found in these regions that scientists did not know of until the 1970s. Another common feature of these boundaries is known as a mid-ocean ridge. These are long mountain chains in the middle of the ocean that demarcate these divergent boundaries. If the crust is splitting apart or diverging, it is known as a rift valley. These are a common one we found in Africa, the African Rift Valley. Another key feature to this is you will also have typically shallow earthquakes. The reason why you have shallow earthquakes here is because the plates are not colliding, they're moving away from each other, but they're not moving away from each other at a constant rate, which creates what are known as fracture zones. So right down the middle here is your divergent boundary. So in these locations, the plates are moving away from each other. However, you'll notice in these locations here, they're not moving away from each other. What has happened, since this plate is moving this direction and this one is moving this direction, you've created a transform boundary. And we'll talk about these more later. But this transform boundary is a grinding side to side, which creates shallow earthquakes. On this global map, then, we can outline major divergent boundaries. For example, this one right here in the middle of the Atlantic Ocean is known as the Mid-Atlantic Ridge, and it's a divergent boundary, moving away from each other. Again, Wegener's Pangea supports this idea as well. Another divergent boundary is over here in the Pacific. This is known as the East Pacific Rise, divergent boundary as well. Rift Valley, an example then would be here in Africa, where we have two plates moving away from each other, and it is a divergent boundary. This mid-ocean ridge right here, if we trace it all the way around, forms the longest mountain chain in the world. Now, that leads us to the question here. If we have areas on the planet where the plates are moving away from each other, is the Earth getting bigger? Or is there something else happening on the opposite sides? At this point, I would like you to conduct the Google Earth earthquake depth and location activity, then come back to the next lecture and we'll discuss the data you found.